All right, we're here to do some momentum problems. This is from Honors Physics Worksheet 1. I'm going to skip the conceptual ones and jump, which I'll do in class live. Let's jump right to the multiple choice, the short calculations. First one says, problem 1 says, Kim holds a 2-kilogram air rifle loosely, so the gun moves independently of the girl, and fires a bullet of mass 1 gram. Muzzle velocity of the bullet is 150 meters per second. What's the rifle's recoil speed? And then part B asks what happens if she grips the rifle tightly and her mass is 48 kilograms. So here we go. So take a look at that one. The way I do momentum problems, typically I'm going to start with the sketch. You're not surprised by that. We always start with the sketch that's before the collision or the interaction of objects and one that's after the interaction. Here we go. So you see, so the first starters, you say, here is, this real quick sketch. Right, you say, hey, there's that rifle. Yeah, right. Before and the bullet in the barrel. Right? And then my after picture, you say, okay. Right? And now the bullet is exiting the barrel, okay, out the muzzle of the barrel, right? Okay, let's go ahead and put in what we know. Let's see. They told us that let's run through. So it's a 2-kilogram air rifle. So the mass of the rifle is 2 kilograms. So they tell us that the mass of the bullet is going to fire a bullet that is 1 gram. So right away, I'm going to say, hey, the mass of the bullet, I'm going to convert to kilograms, right? We always do kilogram for mass. So 1 gram is 0.001 kilograms, right? I divide by 1,000, right? 1,000 grams in a kilogram. And they say, hey, muzzle velocity of the bullet. So the bullet, when it leaves the muzzle, the end of the barrel, you say it's going, the velocity of the barrel, I'm going to say final, after the interaction, is 150 meters per second. I'm going to call that positive. I should really label my coordinate axes, which way I'm calling positive. That's really important in momentum calculations because velocity, momentum, impulse, force, changes in momentum, these are all vectors and have directions. We care about them being positive or negative. They want to know, what is the rifle's recoil speed? So the idea is, at the start, everything's sitting still. At the end, something this bullet gains momentum to the right, something's got to gain momentum to the left to balance it out because there's no outside total force, outside force in the combined system is 0. Point is, recoil is this idea that when you fire this projectile, the projectile goes one way and then moving back, right? The rifle moves back. So we're trying to find this velocity of the rifle at the end. Okay, that's what we're trying to find. Alrighty, so here we go. Running through this in full. The big formula for this unit. You say, oh, well, the big formula for the unit, that is this one. Impulse is equal to the change in the momentum. Okay? Now, one of the key parts of, just like doing an energy problem, one of the key parts is figuring out what your system is going to be. Do we want to analyze just the bullet, just the rifle, the bullet and the rifle together as a system? In this case, we're trying to find out information about the rifle. They give us information about the bullet. I probably want to do a combined system. So I'm going to make my system be the rifle and the bullet. Okay? Now, if I make them a combined system, what outside forces are acting on them? While the bullet's going on the barrel here. You say, well, outside force is acting on the system. I guess there'd be a gravitational force down and a force up from Kim, right? Yes? Kim's hands holding it up. But those forces, they're going to add to 0. So the total outside force on my system, on my combined system, total outside force is 0. So I'm getting 0 is my delta P. All right? Now that delta P, we can go ahead and write this a couple ways. My combined system is the rifle and the bullet. So I could write this as delta P of rifle plus delta P of bullet. Or I could do it as all the finals minus all the initials. Either way you want to write it. I guess I'll split it up into the different objects. So this will be delta P for the rifle and delta P for the bullet. All right. You say, okay. I have an equation for momentum. So momentum is m times v. So I'll substitute that in. Well, actually, let's just write these out. Let's write this. First, let's expand our deltas. This is what we would normally do in an energy problem, right? Expand our deltas. So this will be P rifle final minus P rifle initial plus P bullet final minus P bullet initial. We always do final minus initial, right? Whenever we do a delta, it's always ending minus beginning. Are any of these terms 0? And you say, well, yeah. At the start, they were both sitting still. So my initial values drop out because the initial speed is 0. That's why, right? Those drop out. At the end, then, you say they both have some momentum at the end. This one has momentum to the right. This is momentum to the left. So those two terms are going to stick around. You say, now look, if you look at this, I just have 0 is the final momentum of the rifle plus the final momentum of the bullet. If I add two values and they add to be 0, one's got to be positive, the other one's got to be negative. They got to balance out. So this does, in fact, move backwards, okay, like we anticipated it would. Okay, at this point, let's substitute in P as mv. So you say, okay, this will be mass of the rifle, velocity of the rifle at the end, and this will be mass of the bullet, velocity of the bullet at the end. Okay, at this point, we can put in the values. We are trying to find the velocity of the rifle at the end. That's that recoil velocity of the rifle. We do know the mass of the rifle. It's 2 kilograms. Mass of the bullet, we know is 0.001. Velocity of the bullet at the end, we know is 150. Okay, plug, plug, plug. When you rearrange this, that velocity of the rifle, I got a value of negative 0.075. Okay, and my units, okay, they're going to be in meters per second, of course, it's a velocity. Alrighty. Okay, that negative, you said that negative matters, right? It's showing me that's going opposite the direction that velocity was going. Okay, and that's what we need. Okay, so that's part A of that problem. Okay, that actually was just all part A. Part B now says, okay, what if this time Kim, when she fires the rifle, she hangs onto it tightly. So the bullet goes one way, she's connected to the rifle, so together they recoil back. What's the recoil velocity going to be now, right? Yep. It says the recoil speed is less. Explain why this is true. You say, well, yeah, well, look. Now, instead of it just being the rifle moving back, it's the rifle plus Kim. They're connected together, moving together. So I just made this mass, essentially now it's the mass of the rifle plus the mass of Kim, right? And they tell us that Kim's mass is 48 kilograms, they told us. So together, Kim and the rifle are going to be 50 kilograms. So instead of this being 2 kilograms moving back, now it's 50. But the bullet still has the same momentum gain here, right? So still a gram bullet going 150 meters per second. So to balance it out, bigger mass, we're going to have a smaller velocity. So they still multiply together to be momentum that balances out the momentum of the bullet. So we're expecting a much, much smaller velocity. All right, so the momentum still balances out to 0. So, yep, so we want to know, let's see here, calculate the new recoil speed, and then by what factor is the velocity increased or decreased. So the new recoil speed, I'm going to do the same calculation all the way through. It's just when I get to here, this is rifle and Kim moving together. So when I get to that line right there, instead of being 2 times velocity of the rifle, this is going to be 2 plus 48, okay, combined mass of Kim and the rifle, times that final velocity that Kim and the rifle are going to have, plus that 0.001 times 150. Okay. And so when I did that calculation, I got a velocity of negative 0.003 meters per second. All right. You say, hey, yeah, that is a lot smaller than 0.075, 0.003. You say that's a lot smaller. They say, hey, by what factor is that smaller? And you say, well, what's that factor? You just take the ratio, right? You say, like, okay, if I took 0.075 divided by 0.003. You say, hey, I'm going to see that this one is 1/25th as big as this, okay? Or this one is 25 times bigger than this. You say, well, yeah. So it's a factor by, it's a 1 to 25 ratio. In speeds, right? Or if you want velocities, it's a 1 to 25 ratio. You say, you know why, right? Because we went from having a mass 2 to a mass of combined 50. We multiplied our mass by 25, and so our velocity went down by a factor of 25 to be the same momentum. Right? Make sense? Okay, so that was part B, right? Which I did over here. And that is problem 1. Should I do problem 2 on the same video, just for the heck of it? Yeah, sure, why not? They're small. Okay, let's go ahead and do problem 2 real quick. I think this will be fast. I think maybe I'll put like 2 problems on each video. That's not such a big deal, right? You can fast forward through and find the problem you want. Yeah, let's do that. Just so I'm not juggling so many videos. Here we go. Problem 2. Oh, yeah. Okay, so problem 2 says, in a freight yard, a train is being put together from freight cars, right? An empty freight car coasting at 10 meters per second strikes a loaded car that's stationary and the cars coupled together. So that's going to look something like this. So I've got this car going along. It's going to smack into this other car that's loaded. It's got stuff in it, right? That's my before picture. Afterwards, let's see. Yeah, the cars coupled together. That means they're stuck together, locked together, they're going to move together. So afterwards, right, these guys are connected. We're moving together. Okay, let's see. We know that this one, we know that that's you want to call these A and B? Does that sound good? Okay, so we know that that velocity of A at the start, they tell us it's 10 meters per second. And this one, velocity of B at the start is 0. It starts at rest. Yeah, they tell us that this guy's got a mass of 3,000 kilograms, that empty railroad car. This one, they tell us has a loaded car contains 12,000 kilograms of canned soda. So together, 12,000 kilograms of soda plus 3,000 for the empty car, that would be, the mass of B would be 15,000 kilograms. Right? Mass of A, mass of B. Okay. So they want to know the speed with which the 2 cars move afterwards. They want to know like this velocity, that combined velocity at the end. All right. So here we go. Okay, let's identify to the right as positive. So this will be a positive velocity in our calculations. Make sure we get our sides right. Okay, hey, what do we want to make our system? Well, we're looking for the velocity of the 2 together. So maybe it makes sense to treat them as one big combined system. So this will be A and B will be our system. And we're going to say, hey, F delta T is delta B. Yeah. They say, okay, hey, what outside forces are acting on this? You're like, well, you know, they're rolling along the tracks. There's going to be a gravitational force and a normal force from the track. Those are both going up and down, and they're going to balance out, aren't they? That total force up and down is 0, so our momentum up and down isn't going to change, and they're not so important. Side to side, is there going to be any kind of like friction or like force as it bounces along? Maybe the track's not totally smooth. Like, we're kind of treated to assume. We'll assume it's pretty smooth. The other thing that we're doing here is that when we analyze collisions, we usually are going to look just before the collision and just after the collision, right? Just before and just after. Is that friction force going to have much time to act? No. Are the forces in the collision going to act for long? No. The force in the collision will be way bigger than any friction force. So I think the friction force we can pretty much ignore over that time of the collision is what we're looking at. Now, if we let this roll for a long time, that friction force might start really slowing it down or something. But over this short time, just immediately before to immediately after the collision, it's not going to be big enough to worry about. I think we're pretty much just concerned about the forces from the impact between them. And since we're doing a combined system, the forces of the impact are going to drop out. So we actually have a total outside force is 0. So 0 is my delta P, yeah? Okay. Now, we could split this up and talk about delta P of A and delta P of B, or we could make it as the finals of both minus the initials of both. Either way you want to do it. I'm going to do delta P of car A and the delta P of car B. Okay. Now, you would agree. Let's go ahead and expand those out. Finals minus initials. Always final minus initial. And so you say, all right, this would be momentum of A at the end minus momentum of B. Sorry, momentum of A at the start plus momentum of B at the end minus momentum of B at the start. Are any of these terms 0? You say, yeah, we know that that cart, B, started at rest. So the initial momentum of B is 0. Okay. Let's fill in our values. Okay, we're just going to substitute in now P is MV for each term. And you would say, okay, momentum of A, that's going to be mass of A, velocity of A at the end, minus mass of A, velocity of A at the start, plus momentum of B at the end. That would be mass of B, velocity of B at the end. All right? Now, when I go through and look at these values, you say again, do I know the mass of A? Yes, I do. It's 3,000 kilograms. Do I know the velocity of A at the end? That's what I'm trying to find, is the velocity it has at the end. So I'm trying to find this guy, aren't I? Mass of A, I know what that is. Velocity at the start, I know that's 10. I got that. Mass of B, I know that. Velocity of B at the end, that's what I'm trying to find. You say, but wait a minute, is this really 2 different variables? No, they're moving together at the end. This velocity of A at the end is velocity of B. They're the same variable. It's the same thing. I could just call both of those velocity of the combined thing at the end if I wanted to. That's actually what I'm trying to find. So I just need to isolate that variable, or I can just, right, I can isolate it, get it by itself. Let's just go ahead and put our values in. Here we go. If I crank that out, the mass of A, that's 3,000, times the velocity of A at the end. I'm just going to call it velocity combined final. Minus mass of A, 3,000, times the velocity of A at the start, that's 10 meters per second, plus mass of B, 15,000, times the velocity of B at the end. I'm just calling that the combined velocity of the final. Okay. You say, I can solve that. If I rearrange that, I should get that combined final velocity. I got a value of, when I did it, 1.6666. So about 1 2/3 meters per second. And it did come out to be a positive value, which is reassuring because it's certainly moving in the positive direction this whole time. My total momentum at the start was to the right. This wasn't moving anything, that was to the right. So the total momentum at the end, it better be to the right. Okay. And that is problem 2.